So I wanted to show you around some of the sample problems on your homework in section 2.7. Let me get to that screen, find it again. All right, so we're logging in to your 2.7 homework. Okay, give me just a second. And so I want to talk you through some of the problems, some sample problems. All right, here we go. All right. First of all, it says fill in the blank correctly here. So we just want to verbally do that. That's why I'm doing this way instead this time so you can watch my screen. So we need to understand that the vertical shift are just independent numbers added or subtracted onto the parent function. So here we see an x squared, a parabola, with a independent plus 4. So that's going to move the graph up 4 places. So the graph up, type in 4 to get us started. All right, next type of issue we can have is this little negative sign in front of a function. Independently, -1 multiplied onto the front of any parent function will flip the graph upside down. It's going to turn the graph upside down, or in other words, that would be like reflecting it over the x-axis. Across the x-axis is upside down visually. So we reflect it across, that would be the x-axis for that. Okay, so we got more parts, don't we? Okay. Here we have multiple shifting rules. Here's that independent addition or subtraction that I mentioned earlier. That's the up-down shift. If we have a negative, it's down. If you have a positive, it's up, as you would expect. So the vertical, the up and down shifts are the sign that you see. So that's going to be 6 units down. So that one's 6. And then this part, the +3 that's included inside the parentheses, that's the horizontal shift. That's the left-right shift. So whatever is grouped inside with the action of the x, that can be a parenthesis, an absolute value sign, a radical in the denominator of a fraction. Any way that it's attached to the action of the x, that's a left, right, or horizontal shift. And those are always opposite. So even though it says +3, we're going to move it what we would think would be -3, which is to the left. To the left, 3 places. Okay, next, doing that again, really just the same thing, right? Another example, we have a -5, so it's going to move it +5 or to the right 5. So that goes here. And then the number on the end is +7 is an up 7 places. Okay, next, number 5, we got a whole list of these to see all the different things that can happen, except there's no negative multipliers on any of these to reflect it. So we don't have that going on, but we do have the horizontal shift when we have grouped in with the x. The parent function on all of these is x squared. You see that's the parabola. And then we've got shiftings. Inside the parentheses, that's an opposite sign, so +6, so that's 6 to the right. So which one says 6 to the right? Okay, that's A. A goes with A. Well, okay. Then the next one, -6 on the end, is a vertical shift. So it's an independent -6, and the vertical shifts are as they look. So down 6. So which one says down 6? Let's see, that's E. And then a multiplied 6. Now, a multiplier affects how steep the curve is, or the slope, how much it's stretched. So that's the stretch factor. So it's vertically stretched by a factor of 6. That's answer D. If it's a fraction, it makes it actually look wider. It shrinks the graph when you have a fraction multiplier. We don't see any of those. On D part, inside of the parentheses, so we do the opposite, so that's going to be -6 or to the left by 6. So let's see, that's C. And then the last one, a +6 on the end, that's a vertical up-down shift, and those are as they say, so that's up 6 places, and that's B. Kind of nice overview of the different rules. All right, fantastic. All right, now this one, we're going to talk about symmetry for a little bit, and then we'll get back to those shifting rules. So it wants us to plot the point -5, 5. So let's start with that. Let's plot back 4, down 5. Okay, I need to hit save. Check my answer. Okay, fantastic. This takes you through a series of questions, so we have to say continue. All right, then A part wants it to be symmetric with the x-axis. So when it says symmetric with the x-axis, here's our x-axis. We're going to flip this across the x-axis. What would it look like if you folded your paper along the x-axis? Where would this point lie? So it would lie up here. And basically, whenever you're symmetric with the x-axis, you change the sign of the y variable to +5. So it's kind of backwards. If you're doing x-axis symmetry, you change the y to -y to get its sister point or its reflected point. So it's still going to be at -4, but it's at +5. Okay, well done. Okay, let's continue. We're going to practice all the symmetries. To do symmetric with the y-axis would be like you fold your graph or fold your paper along the y-axis, and so this would then flip over to this side across the y-axis. So it's going to be a point over here. Let's blow this up. All right, so where would that be? It would be +4 and -5. Notice we changed the sign of the x to the opposite. Again, it's kind of backwards. If we're doing symmetric with the y-axis, the x changes to the opposite sign. When we're doing symmetric with the x-axis, the y becomes the opposite sign. And that's how we check it algebraically in the next couple of examples. And you might remember from the lecture, that's kind of a thing for proving y-axis, x-axis symmetry. If it has a sister point, oh, did I not finish that one? I don't see it. I better do that again. Over 4, down 5, save. Maybe I didn't hit save. Oh, I did the wrong problem. I had saved on B part. I'm on C part now, right? Sorry about that. I lost my spot while I was talking. So I don't see a place to hit clear, so maybe it'll just let me move that point. So we're on the origin question. To do symmetry with the origin, that's a rotation. So I wish that point wasn't there to look at. But when we rotate, we want to move the graph through 2 quadrants. So it's going to land up here somewhere. And the rule is symmetry with the origin is a rotation of 180 degrees. And it changes the sign of both these both of these coordinates. So it becomes +4, +5. Let's see if I can move that around. Okay, good. It's moving. So move it around 180 degrees and boom, it comes over here to, let's see, is that +4, +5. And that would be its sister or symmetric point if you were to rotate that up 2 quadrants. And again, it is a matter of changing, if you're doing symmetric with the origin, changing the x to its opposite and the y to its opposite gives you its sister point or its symmetric point with that symmetry. All right, nice work. All right, moving on. Now, here's some quicker questions about symmetry. Which symmetry do you think this one has? And again, the way you can prove this is if you were to change this x to a -x and it makes no difference in the equation, which is what happens whenever you have these even functions, when they're all even exponents on the x, because a negative to an even exponent or a positive, it will not matter. You get the same result, a sister point to it, you should say. So again, x to -x proves y-axis origin. Also, if you were to think about this, we might know this graph. That's one of our parabolas and then shifted up 19 places. So you could look at that on a graph and see that it is going to fold along the y-axis. And next, this is actually a kind of a special case. It takes us back to an equation that we learned in section 2.2, which this is a circle. You might remember if you have x squared plus y squared equals a constant, that's the radius squared. So this is a circle with no offset. It's centered at the origin. So it has all the symmetries. You can rotate it any amount of degrees and it looks exactly the same. And you can fold it along the x-axis and it meets. You can fold it along the y-axis and it meets. So it has all 3 of these. You can check all 3 of those symmetries. Also, to prove it, if you use the rule, if x is changed to -x and it makes no difference in the equivalent equation, that proves y-axis symmetry. If you can change y to -y and it doesn't matter, in all of the variables, you can change all your y's to -y. Here we just have the 1. and it would not matter because it's squared. And then to check for origin, you change both the x and the y to their opposite, and it doesn't matter. So all of those check out. Also visually, if you know that's a circle, you'll know it's a very symmetric figure where it's centered at the origin. Okay, number 9, again with the symmetry. So this one is actually an origin symmetry because it has all odd exponents. And we learn in the lecture and the discussion, if you have an odd-powered, all odd-powered, it's called an odd function, and odd functions are symmetric with the origin. Officially, the definition is if you can change x to negative x, so both of these x's, if you made both of those negative, and the y to negative y, and then you looked at that to see if it's equivalent to the original equation, it would be, because you could divide each one of those back out by the negative and prove that. But anyway, you can also remember if you have all odd exponents, it's an odd function, and odd functions are symmetric with the origin. Also, you might graph it and look at it and see if you think it rotates and looks the same if you rotate it 180 degrees. All right, maybe this is the last one of the symmetry. This one is a type of parabola. If you were to graph that parabola, it's not really in the shifting rule format for us to tell exactly what it looks like, nothing that we've done in Chapter 2. This is exactly what we're going to start in 3.1, talking about general quadratics, how to graph those. You would find that it has lost all of its symmetry. This graph has been shifted from the origin left-right. You can't really tell it in this form it's in, but if you sketched a graph, you could tell it then. And also, by that rule I keep talking about, if you change the x to negative x, it does make a difference. In this one, it does not. A negative squared would be the same as a positive squared, but this x is to the first power. So if we change it to the opposite sign, it's really going to change it to the opposite sign and change the look of the equation. So it would not be an equivalent equation. So in general, though, I can tell you, if you have even exponents and odd exponents, and this x is to the first power, even though you don't see an exponent, it's understood to be the first. So we have even and odd, a mixture of even and odd, you lose your symmetry in general there. So no symmetry for various reasons. Oh, there's another. Okay. So this is probably like a duh question. If you look at this, you probably, with those 3 choices, pick odd, I think. But the reason we would say it's an odd function is if all of the exponents are odd exponents. So the 7, x to the 7th, x to the 5th, totally just odd exponents, that makes it an odd function. If you have a mix of some even and some odd, you lose your symmetry there. You either have to be all odd exponents, like we see here, to be odd, or all even exponents to be an even function. And if there's a mixture of the two, it's a neither. All right, so now we're going to graph some of these with the shifting rules that we started with at the beginning. So we should have an idea about what type of shifting rule this is, where it's at the end, an independent add or subtract is a vertical shift. First of all, we need to pick up the right figure and know that the parent function is a parabola. Now, try as you might, this drives my students crazy in the past, so I feel for you if you're having trouble. It doesn't matter where you click. You can try to put it where you want it, but when you click, it draws it in like its standard basic form. So you can't control that. Just let that go. Just click anywhere. Then to move it, you have to use these tools down here to show it, understand the reflections and the shiftings. So the only thing happening here, so don't bother the vertical or horizontal stretch. That happens if there's a multiplier in front of it. So don't do that. We only want to do the shift, which is this -5. And it is moved down 5 places. So we need to tell it to shift it vertically, up, down by 5. And that's all that's happening here. So hit save and it moves it. And then we check it. Okay, and that's how these last few problems are. Program's moving a little slow tonight. Okay, next one, similar. The shape, though, that absolute value of x is the V shape. So we need to pick up the right parent function. Click anywhere. Oh, did I pick it up? Well, I lied to you. Maybe I clicked it twice. Let me try that again. Pick up the V shape. Click. Oh, this one is going to let me move it around, so I apologize. I thought they were all kind of the same.